And please, because I'm not feeling well, if it suddenly you can't hear anything or anything like that, please let me know. All right, so we're doing the Cisco Module 8 network layer tonight. And this one is out in the PowerPoints, so you can go out and take a look. There's some really good graphics on this one. So I would go out and snag some of those. All right, so we're going over the OSI network layer. I don't know why it's spaced out like that in that slide. That's kind of interesting, but okay. So this one, the network layer provides services to allow end devices to exchange data. So IPv4 and IPv6 are the principal network layer communication protocols. The network layer performs 4 basic operations, and this is one of those ones that you want to put on a flashcard or your notes or whatever. So remember these 4 basic operations: addressing end devices, encapsulation, routing, decapsulation. Remember that. IP encapsulation. Now I will say that I like Cisco's slides for their how to do stuff on there a little bit better for the graphics. So IP encapsulates the transport layer segment. IP can either use IPv4 or IPv6 packet and not impact the layer 4 segment. IP packet will be examined by all layer 3 devices as it traverses the network. The IP addressing does not change from source to destination. At least it shouldn't change. If it does change, something is very wrong, and usually there's something like a man-in-the-middle attack or something like that causing problems. NAT does chain addresses. We kind of talked about that one. That's the one where it you use the IP address internally. You have your private and public address. That's what NAT's talking about. So that's the only one that habitually changes. Does that make sense? Yep. Okay, so characteristics of IP. IP is meant to have low overhead and can be described as connectionless, best effort, media independent. Okay, IP connectionless. This means it does not establish a connection with the destination before sending the packet. There's no control information needed. They're talking about that CSEC stuff like we were talking about with the 3-way handshake. The destination will receive the packet when it arrives, but no pre-notifications are sent by IP. If there is a need for connection-oriented traffic, then another protocol will handle this, typically the TCP at the transport layer. So that's why you see TCP/IP, because IP doesn't do this, TCP doesn't do this, so you have to put them together to get the whole shebang. Best effort. So what they're talking about with best effort, IP does not guarantee delivery of the packet. It has reduced overhead since there is no mechanism to resend that data if it is not received. It does not expect acknowledgements, and it does not know if the other device is operational or if it received the packet. So this is just a little quick thing that shows packets were routed through the network quickly. Some packets can be lost en route, and then it just shows kind of a little graphic of how everything's going around the circle here. So what it means by media independent, it is unreliable. It cannot manage or fix undelivered or corrupted packets. They're just out there. It cannot retransmit if there's an error, cannot realign out of sequence packets. See what I mean about my email having a distinctive sound? I don't know if you could hear that or not. IP cannot transmit after an error. It must rely on other protocols for these functions. Sorry, I lost my place. IP is media independent. It does not concern itself with the type of frame required at the data link layer or the media type at the physical layer. It can be sent over any media type. By that, it means copper, fiber, wireless, so it doesn't matter. The network layer will establish maximum transmission unit, or MTU. The network layer receives this from control information sent by the data link layer. The network then establishes the MTU size. Fragmentation is when layer 3 splits the packet into smaller units. Fragmenting causes latency. IPv6 does not fragment packets. An example, router goes from Ethernet to a slow WAN with a smaller MTU. And this is a graphic showing, it goes up from copper Ethernet, copper serial, optic fiber, and then drops down to copper Ethernet and then goes over wireless. So it shows some possible ways in which it might be split out. Is that making sense to everybody so far? Thumbs up, thumbs down. Everyone's asleep. We're good. Okay. Packet headers. This is the primary communication protocol for the network layer. The network header has many purposes. It ensures the packet is sent to the correct direction to your destination. It contains information for the network layer processing in various fields. The information in the header is used by all layer 3 devices that handle the packet. IPv4 packet header fields. The IPv4 network header characteristics. It is in binary, contains several fields of information. Diagram is read from left to right, 4 bytes per line. The two most important fields are the source and destination. Protocols may have one or more functions. And then you have this nice little example over here showing your byte 1, byte 2, byte 3, byte 4, and examples of what that would look like for the IPv4 network header. And then you have a little table here for significant fields in the IPv4 header functions, descriptions. So the first function, version, for version 4 as opposed to version 6, a 4-bit field, and that's in binary there. Differentiated service used for QoS. And then they have TOS for type of service, header checksums to detect corruption in the IPv4 header, TTL, if you're wondering, if you didn't know what TTL is, time to live. That is telling you how many hops it's supposed to take. So basically, if it takes too long, it'll time out. And then you have usually if you have, depending on what program you're using, things like that, you set your time to live. If you're doing like a check on something, and then if it goes over the time to live, it gives you all sorts of information that way too. When it so layer 3 hop count, when it becomes 0, the router will discard the packet. Protocol IDs, next level protocols. So that's your ICMP, TCP, UDP, all the other ones. Source IPv4 address, 32-bit source address, destination IPv4 address, and that's your 32-bit destination address. Okay, so big limitations of IPv4 are depletion, and that's really the big one right there, address depletion. And this is why IPv6 was made. We've run out of IPv4 addressing. There's just not enough room. Internet, networking, things like that just exploded. Lack of end-to-end connectivity. To make IPv4 survive this long, private addressing and NAT were created. This ended direct communication with public addressing. Increased network complexity. So NAT was meant as a temporary solution and creates issues on the network as a side effect of manipulating the network headers addressing. NAT causes latency and troubleshooting issues. All right, next we're on to IPv6. Before we hit that, are there any questions about the IPv4 stuff that we just covered? Yay, nay? Everyone good? I was going to say, I think some of this is pretty much just rehashing what you guys have already been going over. Okay, IPv6 overview. It was developed by the IETF, the Internet Engineering Task Force. It was developed to overcome the limitations of IPv4, and some of the improvements it provides are increased address space. So IPv4 is 32-bit and IPv6 is 128-bit. Improved packet handling. So it has simplified headers with fewer fields, and it eliminates the need for NAT. Since there's a huge amount of addressing, there's no need to use private addressing internally and be mapped to the shared public address. So this is a little chart showing the IPv4 and 6 space comparisons by NAT. Yeah, but you know, what's funny is I don't know if it's just because we're in Idaho and I've had experience with so many legacy systems. By that I mean old. I've seen NAT and old IPv4 stuff a lot, so it's still out there. So yeah, here's your IPv4 and 6 addressing: number, name, scientific notation, and number of zeros. It's a lot easier to write, as you can see in your scientific notation. And don't feel bad if you don't know the number names like sextillion, septillion, octillion. Don't feel bad if you don't remember those. Okay, so IPv4 versus IPv6 header fields. So since 6 is simplified, it's simplified but not smaller. The header is fixed at 40 bytes or octets long. Several IPv4 fields were removed to improve performance. Some fields were removed to improve, like some specific fields were, let's see, flag, fragment, offset, and header checksum. So here you can see, if you remember the other one, it had all those little chunks of tons of different information. As you can see, you still have your byte 1, 2, 3, 4, but you have significantly less information fields. So here's your significant fields table, just like in the other one. So version, this is for 6 instead of 4. That's what they were talking about in the other one. Traffic class, QoS is what that one's used for. Flow label, this informs the device to handle identical flow labels the same way, and it's a 20-bit field. Payload length, this 16-bit field indicates the length of the data portion or payload of the IPv6 packet. Next header, ID's next level protocol, and that's the same like the ICMP, TCP, UDP thing. Hop limit, source, and destination, just like they had in IPv4. It may also contain extension headers. Some extension header characteristics provide optional network layer information. They are optional, are placed between IPv4 header and payload, may be used for fragmentation, security, mobility, support, etc. Okay, so I think I'll dig up some, have any of you, I think there were some people that have used Wireshark. Are there some people that have used Wireshark in here before? Yay, nay, Wireshark? Yep, Mike's used it. Some people have heard of it. Okay, well, you'll get familiar with it. We'll get to use it later on, but I will go dig up a video for you guys so you can see an example of a Wireshark packet trace. Let me make a quick note of that. Okay. Host forwarding. So packets are always created at the source. Each host device creates their own routing table. A host sends packets to the following: itself, local hosts, and remote hosts. And then you'll see your graphic down there below where you have your local host, remote host graphic. The source device determines whether the destination is local or remote. And then method of determination, IPv4 source uses its own IP address and subnet mask, along with the destination IP address. IPv6 source uses the network address and prefix advertised by a local router. Local traffic is dumped out the host interface, to be handled by an intermediary device. Remote traffic is forwarded directly to the default gateway on the LAN. A default gateway, how host routes default gateway. Router or layer 3 switch can be default gateway. Features of a default gateway or DGW. It must have an IP address in the same range as the rest of the LAN. It can accept data from the LAN and is capable of forwarding traffic off of the LAN. It can route to other networks. If a device has no default gateway or a bad default gateway, its traffic will not be able to leave the LAN. How a host routes to default gateway. The host will know the default gateway either statically or through DHCP. IPv6 sends the default gateway through a router solicitation. If you remember that yesterday where they were talking about neighboring devices and then router solicitation commands, or it can be configured manually. Really just depends on what type of network analyst you have or admin when they're set it up, whether they prefer to do router solicitation or manual configuration. A DGW is static route, which will be a last resort route in the routing table. All devices on the LAN will need the DGW of the router if they intend to send traffic remotely. And then this just has your direct, connect, local network, remote network, and then an example of how everything's supposed to go through. Host routing tables on Windows, route print or netstat-r to display the PC routing table. And you can see that right there. It's a command line one that you'll see netstat --r, and it runs, it's another one of those you need to run in the command prompt ones. The 3 sections are the interface list, and that's all your potential interfaces and MAC addresses. IPv4 routing table and IPv6 routing table. Okay, router packet forwarding decision. So what happens when the router receives the frame from the host device? So the packet arrives on the gigabit Ethernet interface, router R1. R1 de-encapsulates the layer 2 Ethernet header and trailer. Router R1 examines the destination IPv4 address of the packet and searches for the best match in its IPv4 routing table. The route entry indicates that this packet is to be forwarded to router R2, and you can see the labels are up here, R1, R2. Router R1 encapsulates the packet into a new Ethernet header trailer and forwards the packet to the next hop, router R2. So you'll see up here where it has the R1, R2, and then it's got your little email things talking about the packets. There's 3 types of routes in a router's routing table. Directly connected, these routes are automatically added by the router, provided the interface is active and has addressing. Remote, these are the routes the router does not have a direct connection and may be learned manually with static dynamically by using a routing protocol to have the routers share their information with each other. And default route. This forwards all traffic to a specific direction when there is not a match in the routing table. So basically it goes, there's nothing in the routing table, everything goes this way. So that's what it's saying on default route. Static route must be configured manually, must be adjusted manually by the administrator if there's any sort of changes. It's really good for small, non-redundant networks, and it's often used in conjunction with dynamic routing protocols for configuring a default route. And then they just have kind of an example up here of how that works. Dynamic routing discovers remote networks, maintains up-to-date information, chooses the best path to the destination, finds new best paths when there is a topology change, and dynamic routing can also share static default routes with other routers. So as you can see there, it's got the path and then the previous example of previous and new, and it's that's why a lot of places use dynamic routing when they can. And then there are, of course, things that require static routing, but for expediency, a lot of times they try to use dynamic as much as possible. Okay, IPv4 routing tables. So the show IP route command shows the following route sources. L, directly connected local interface IP address. C, directly connected network. S, static route was manually configured by an administrator. O, OSFP. D, EIGRP. This command shows types of routes: directly connected, remote routes, default routes. And then you see over here, basically it looks like a help entry that shows how to do that with the routing table. Remember, this is Cisco based, so there are other types of things if you're working with different types of routers. For example, the district that I was at was mostly Cisco based, and then they switched over to Juniper, and it was a different ecosystem. Okay. So this is just an example of everything that came through here. So remember, an IP is connectionless, best effort, and media independent. It does not guarantee packet delivery. IPv4 packet headers consist of fields containing information about the packet. IPv6 overcomes IPv4's lack of end-to-end connectivity and increased network complexity. A device will determine if a destination is itself another local host and a remote host. A default gateway is router that is part of the LAN, I think they mean is a router, and will be used as a door to other networks. The routing table contains a list of all known network addresses and prefixes where to forward the packet. The router uses longest subnet mask or prefix match. The routing table has 3 types of route entries: directly connected networks, remote networks, and default route. Okay. So that's it for that. Are there any questions about what we just went over? I know it's not super fun, fancy stuff, but it's just one of those repetitive information things that the more you go over it, the better it is. Okay, so very funny, Mike. I'm a little slow, so for a second I was like, do you have a real question? Wait, no, okay. Tell I'm doing great. Okay, so if nobody has any questions, then I'm going to end the recording.